Welcome to BrainOmega, PyTorch Tutorial 4. Today we'll build a small but realistic regression project end-to-end, locking in deterministic runs, a clean data pipeline with proper train, val, test splits, and efficient mini-batches via DataLoaders. We'll train with mixed precision on GPU, use learning rate scheduling, apply early stopping with best model checkpointing, and keep training stable with gradient clipping. All metrics flow into TensorBoard so you can see exactly what's happening. By the end, you'll have a reliable, repeatable workflow you can trust and reuse on your next project. When we build machine learning projects, one of the most important things to aim for is reproducibility. That simply means if we or someone else run this exact project tomorrow, we should get the same results. Without reproducibility, it's hard to debug, compare experiments, or build trust in our models. To achieve this, we need to make sure that all sources of randomness, whether they come from Python, NumPy, or PyTorch, are controlled. That's why we set a seed value and force PyTorch to use deterministic algorithms whenever possible. A seed acts like a reference point. Once you fix it, random number generators will always produce the same random sequence of numbers. Before we even touch CUDA, the GPU backend, we configure some environment variables. For example, cublasconfig helps ensure that operations on the GPU, like matrix multiplications, behave deterministically. In practice, this can slightly reduce performance or even cause issues on certain systems, so it's something you can comment out if needed. After that, we import the usual suspects, Python's random, NumPy, and PyTorch. Notice how we also bring in useful PyTorch utilities such as DataLoader, Tensor Dataset, and Summary Writer for TensorBoard logging. We'll use those later when we move beyond reproducibility and start training. The core of our reproducibility setup is the seed everything function. Here, we call the seeding functions for Python's random, NumPy, and both CPU and GPU seeds in PyTorch. We also configure the backend flags, disabling benchmark mode, and enabling deterministic mode for QDNN. This ensures PyTorch doesn't silently switch between faster but non-deterministic algorithms. Finally, we attempt to enforce deterministic algorithms globally with torch.use_deterministic algorithms, open parenthesis, true close parenthesis. Depending on your hardware and PyTorch version, some operations may not support this mode, so you might see a warning, but that's expected. Next, we decide where our model will run, either on GPU if one is available or on CPU otherwise. We store this in a device object. Since GPUs support automatic mixed precision, AMP, we also set a flag use_amp to true when running on CUDA. AMP lets us speed up training and save memory by mixing float 16 and float 32 operations safely. Finally, we make sure PyTorch's default data type is set to float 32. This is the standard choice for most deep learning tasks, and being explicit about it avoids subtle bugs when working with tensors. At this point, we've laid down the foundation, a deterministic, reproducible, and device-aware environment. Everything we do from here, data loading, model training, or evaluation, will be consistent and repeatable across runs. That's a huge win for both beginners and advanced practitioners because it builds confidence that the results come from our design choices, not from hidden randomness. Now that our environment is reproducible, the next step is to bring in some real data. For this tutorial, we'll use a classic dataset from scikit-learn, the diabetes dataset. It's small, only 442 samples, each with 10 input features, but it's perfect for practicing regression workflows. We load the features X and targets Y using load diabetes, making sure to convert them into float 32 NumPy arrays right away. This is important because PyTorch models expect float 32 by default, and keeping types consistent prevents hidden errors later. Before training, we also want to make sure our features are standardized. That means we scale them so that each feature has zero mean and unit variance. Why does this matter? Neural networks, especially multi-layer perceptrons, MLPs, train more stably and converge faster when inputs are on a similar scale. For this, we use scikit-learn's standard scaler. After scaling, we convert the NumPy arrays into PyTorch tensors so that they're ready to be wrapped in datasets and DataLoaders. Next, we split our dataset into train, validation, and test sets. A common choice is 70% for training, 15% for validation, and 15% for testing. Training data is used to update model weights. Validation data is used to tune hyperparameters and detect overfitting, and the test set is held back until the very end to evaluate performance fairly. We create a tensor dataset from our features and labels, then use random split to divide it. To keep splits reproducible, we set a manual seed in the generator. This way, you'll always get the same exact split across runs. Once we have datasets, we set up DataLoaders to feed mini-batches efficiently into the model. Mini-batching helps speed up training by leveraging vectorized operations and GPU parallelism, while also smoothing out noisy updates compared to single-sample training. For training, we shuffle the data at each epoch to reduce bias, while validation and test sets stay in a fixed order. To make things efficient on GPU, we enable pin memory so that batches are transferred faster to CUDA. We also define a worker init.fn to seed each DataLoader worker process separately. This ensures that even parallel data loading is reproducible. We choose a batch size of 64 for training and slightly larger batches of 128 for validation and testing, since evaluation doesn't require gradient computation and can be done more efficiently. Finally, we check the lengths of our data loaders to confirm that everything is split correctly. At this stage, we have a tiny regression dataset prepared with proper pre-processing, clean splits, and efficient mini-batch pipelines, exactly the kind of foundation you want for building trustworthy experiments. With the data pipeline ready, we can define a simple yet solid multi-layer perceptron, MLP, for regression. Our regressor class subclasses nn.module and builds the network inside a nn.sequential container to keep the forward pass clean and readable. The first layer, nn.linear open parenthesis in underscore dim comma, hidden close parenthesis, projects the 10 standardized input features into a higher dimensional hidden space, 64 by default. Right after that, we add nn.batchNorm 1D open parenthesis, hidden close parenthesis, which normalizes activations per feature across the batch. On tabular data, this often stabilizes training and lets us use slightly higher learning rates. We then apply a nonlinearity with nn.ReLU open parenthesis, close parenthesis, so the model can learn curved nonlinear relationships, and follow with nn.dropout open parenthesis, dropout close parenthesis as a lightweight regularizer that randomly zeroes some activations during training to reduce overfitting. The middle block repeats a hidden linear ReLU stack to increase model capacity without making it overly deep. This two hidden layer pattern is a dependable default for small tabular problems. Finally, a last nn.linear hidden one serves as the regression head, outputting a single continuous value per sample. No activation here because regression targets aren't bounded. If you find the model underfitting, high bias, you can raise hidden, for example 128, or add another hidden block. If it's overfitting, validation loss worse than training, consider increasing dropout, for example 0.2 to 0.3, or adding weight decay in the optimizer later. After constructing the module, we move it to the correct compute device with dot to device, which ensures all parameters and incoming tensors live on the same CPU/GPU. This avoids subtle runtime errors and keeps data transfers efficient. Printing some p.numel for p in model.parameters gives a quick parameter count, a helpful sanity check on model size and memory needs, while printing the model itself shows a readable layer-by-layer summary. By default, PyTorch initializes weights with sensible heuristics, for example chiming/he initialization where appropriate, which generally work well with ReLU networks. You can swap in a custom initializer later if you want tighter control. In short, this architecture is intentionally small, regularized, and easy to train. Batch norm for stability, ReLU for nonlinearity, dropout for generalization, and a single unit head for scalar regression. It's a practical baseline, simple enough for beginners to understand, yet strong enough to produce reliable results on the standardized diabetes dataset. With the model defined, we need two ingredients to make learning happen: a loss function to tell the network how wrong it is, and an optimizer to nudge the weights in the right direction. For regression, we'll use mean squared error. That's nn.mse loss in code. Think of it as measuring the average of the squared mistakes between our predictions and the true values. Squaring means bigger mistakes count extra, which usually gives us smoother fits. If you ever find that a few outliers are throwing things off, switch to smooth L1 loss, also called Huber, which is a bit more forgiving. To update the weights, we'll use Adam W with a learning rate of 1e-2, that's 0.01, and a weight decay of 1e-3, that's 0.001. Adam W is Adam with decoupled weight decay. Think of it as a gentle regularizer that helps the model generalize. This learning rate is intentionally a little brisk because our features are standardized and we're using batch normalization. If training looks jittery, just dial it down to 3e-3, 0.003. Learning rates don't need to stay fixed, so we'll add a scheduler called Reduce LRO on plateau. It watches the validation loss and, if progress stalls for about 10 checks in a row, it cuts the learning rate in half. We say it runs in min mode because lower loss is better. I like to think of this as an auto brake. Start fast, then slow down as we approach the good stuff, often landing in a better spot without manual tuning. One practical note, this scheduler only reacts when you call scheduler.step open parenthesis val_loss close parenthesis after each validation phase, so we'll wire that into the training loop. Loss is what the optimizer chases. Metrics are how we, as humans, judge progress. Our regression metrics helper builds a small dashboard you can log to TensorBoard or print each epoch. We'll track MSE, the same quantity as the loss, just for reference. MAE, mean absolute error, easy to read because it's in the same units as the target, and RMSE, root mean squared error, also in target units, so it's intuitive. We'll also report R squared. In plain English, R squared tells you how much of the variation in the target your model is explaining. Close to 1 means it's explaining most of it. Around 0 means it's no better than always predicting the average. Negative means it's actually worse than that simple baseline. We add a tiny safety constant internally to avoid weird edge cases if the target barely varies. You'll notice the metric function expects CPU tensors. That's on purpose. Moving small tensors to the CPU before logging keeps GPU memory free and avoids blocking the GPU with light bookkeeping work. In practice, after each evaluation step, we detach the predictions, move them to CPU, and pass them into the metrics function. The function returns a neat dictionary, perfect for TensorBoard, so each value becomes its own time series. That way you can spot patterns like loss is dropping but MAE has stalled, or R squared starts climbing once the scheduler kicks in. Put it all together and you get a clean, reusable pattern. MSE guides the optimizer. Atom W plus weight decay gives stable, regularized updates. The plateau scheduler adapts the learning rate as progress slows. And a compact metrics panel, MAE, MSE, RMSE, R squared, gives you human-friendly feedback. Separating optimize with loss from judge with metrics is a best practice you can carry into almost any regression project. Early stopping is our safety net against overfitting and wasted compute. Think of it like this. After every validation check, we ask, did the model genuinely get better? If yes, we reset the weight counter and stash away a copy of the current best weights. If not, we increment the weight counter. Once we've waited too long without real improvement, defined by a patience window, we stop training early. In this class, patience is how many validation rounds we're willing to wait, and min delta is the tiniest improvement we still consider real, so tiny noise doesn't fool us. We track the best validation loss we've seen, self.best, and when a new best shows up, we clone the model's state dict to CPU for safekeeping, self.best state. The step method returns two flags, whether we improve this round and whether it's time to stop because we've exceeded patience. In our setup, we create early stopper with a patience of 30 and a min delta of 1 E-6, that's 0.1. 0.00001, which is conservative and works well for small tabular problems. We also set best path equals best_model.pth. So later in the loop, we can save the best checkpoint with torch.save_early_stopper.best_state, best path. Right when we see an improvement or after training finishes, we can restore those best weights with model.loadStateDict_early_stopper.best_state before doing a final test. The result, training stops at the right time, and you walk away with the best model you saw along the way, not just the last one. We're ready to train, so first we set up TensorBoard logging with a summary writer. This lets us record losses, metrics, and the learning rate as the run progresses, so you can visualize everything later. We'll train for up to 300 epochs, and we'll keep training stable with gradient clipping. Here we cap the total gradient norm at 1.0, which helps prevent those rare but destructive exploding gradient steps. Because we may be on a GPU, we also prepare automatic mixed precision. If CUDA is available and we chose to use AMP earlier, we create a grad scaler to safely scale the loss and keep low precision math numerically stable. Alongside that, we define an autocast helper that returns the right context manager. On GPU with AMP, it uses autocast, so many ops run in faster, float 16 under the hood, and on CPU or when AMP is off, it becomes a harmless no-op. This way, the rest of our training code stays clean and identical across devices. Training and validation flow through a single function, run epoch, which takes a data loader and a flag that says whether we're training or just evaluating. We switch the model into the correct mode with model.train, open parenthesis mode equals train, close parenthesis. Training mode enables layers like dropout and batch norm to behave properly, while evaluation mode freezes their behavior for consistent validation. For each mini-batch, we move inputs and targets to the right device with non-blocking equals true to speed up transfers when pinned memory is enabled. In training, we start by zeroing the gradients efficiently with set to none equals true, then run the forward pass inside autocast so AMP can kick in on GPU. We compute the loss, and if AMP is active, we scale it and backpropagate through the scaled value, clip the gradients to our max norm, take an optimizer step via the scaler, and then update the scaler. If AMP isn't active, we do the same steps without scaling. During validation, we wrap the forward pass in Torch inference mode to turn off gradient tracking and save memory and time. After each batch, we accumulate the loss for averaging, and we also collect metrics on the CPU. We detach the predictions and targets, move them to the CPU, and send them to our regression metrics helper. Doing the bookkeeping on the CPU keeps the GPU focused on the heavy lifting. At the end of the epoch, we average the loss and the metric values across all batches, so a single number represents that epoch's training or validation performance. The main training loop ties everything together. For each epoch, we run one pass over the training loader and one over the validation loader. Then we step the learning rate scheduler with the latest validation loss. This is the plateau scheduler that will cut the LR in half if progress stalls for a while. We log everything to TensorBoard, training loss, validation loss, each metric for train and val, and the current learning rate. Next comes early stopping. We feed the validation loss and model to our stopper. If we truly improved, we save a fresh copy of the best weights to disk. If we've gone too long without improvement, we trigger an early stop to avoid wasted compute. Every 20 epochs, or right when early stopping trips, we print a concise status line with train loss, val loss, validation R squared, and the current learning rate, plus a little star when we've just hit a new best. Finally, we measure how long training took, close the writer to flush any remaining logs, and print a tidy summary. The result is a training loop that's fast on GPU, safe with mixed precision, protected by gradient clipping and early stopping, adaptive with a plateau scheduler, and fully observable in TensorBoard. It's the kind of loop you can trust and reuse in many future projects. If you're in Google Colab, you can open TensorBoard right inside the notebook. First, we load the TensorBoard extension, and then we point it to the folder where our logs are being written. In our case, that's the runs directory we set in Summary Writer. So run these two lines. Load the TensorBoard extension, then TensorBoard with logdir equals runs. After a moment, a panel will appear showing your dashboards. Once it's up, click into Scalars to see your training loss and validation loss over time. You'll also find the metrics we logged, MAE, MSE, RMSE, and R squared, as separate curves, plus the learning rate so you can watch the scheduler kick in. You can compare multiple runs, smooth the curves to reduce noise, and zoom into specific epochs. If you don't see anything yet, make sure you've run the training cell first so it creates log files. If the embedded view doesn't load in Colab, look for the Open in New tab link that appears under the panel. Working locally instead of Colab? You can launch TensorBoard from a terminal with TensorBoard-logdir runs and then open the shown URL in your browser. The experience is the same. Loss curves, metrics, and learning rate all in one place. Pro tip: name different experiments with unique subfolders inside runs. For example, run/xp_lr_1e-2. So TensorBoard can overlay their curves and you can compare settings at a glance. That's it. 2 lines in Colab to bring your training to life visually, and an easy terminal command if you're running on your own machine. First, we load the best model weights we saved during training. That file, best_model.pth, contains a snapshot of the model at the moment it performed best on the validation set. We load it to the CPU to be safe and compatible on any machine, then move the model back to the correct device, CPU or GPU. We also switch the model to evaluation mode with model.eval. This is important. It tells layers like batch norm and dropout to behave in their inference settings, so results are stable and comparable. Now we run our test set. This is data the model has never seen during training or validation, so it's the fairest way to judge real performance. We wrap the loop in Torch inference mode to turn off gradient tracking. This makes evaluation faster and uses less memory. For each mini-batch, we send inputs and targets to the device, make predictions, compute the loss for reference, and collect our metrics on the CPU. When the loop finishes, we average the loss and each metric across all test batches so we get a single, easy-to-read summary. Finally, we print a short report. Mean squared error, root mean squared error, mean absolute error, and R-squared. Remember the intuition. MAE and RMSE are in the same units as your target, so they're easy to interpret. Lower is better. R-squared tells you how much of the variation in the target your model explains. Close to 1 is strong, around 0 is no better than predicting the average, and negative means worse than that simple baseline. With this, you've closed the loop. You trained with early stopping and checkpointing, restored the best version of your model, and measured its true performance on unseen data. To wrap up, let's visualize how our model's predictions compare to the real target values on the test set. First, we switch the model to evaluation mode and turn on inference_mode so everything runs fast and memory light. We loop over the test data loader, move each batch to the right device, generate predictions, and immediately bring those predictions back to the CPU. We collect all predictions and all true targets into 2 big arrays so we can plot them at once. Now we make a scatter plot where each point shows true value on the x-axis and predicted value on the y-axis. If the model were perfect, every point would sit exactly on the diagonal line where prediction equals truth. So we draw that reference line, then scatter our points to see how closely they hug it. Tight clustering around the line means strong performance. A lot of vertical spread means the model is off by more in those regions. You can also look for patterns, like curved shapes or gaps, that might hint at underfitting, overfitting, or missing features. A couple of tips. If the points look too dense, try reducing the marker size or adding a little transparency. If the range is very narrow, expand the figure size or set x/y limits to match the mean and max of your data. This one simple chart gives you an intuitive, at-a-glance check of calibration. Are predictions systematically high or low? And error spread across the target range, making it a great final sanity check before you ship your model.